Last time, we discussed Kirchhoff's laws, but I didn't say anything about how inductors work. Today we are going to talk about the role that inductors play in circuits and how inductors complete the analogy between mechanical and electrical systems. Inductors have a simple constitutive law that relates the voltage across the inductor to the time derivative of the current through the inductor. That is, the voltage is equal to Li prime. Here I am using the prime notation for the derivative so that the dot over the I is not confused with the time derivative. This time derivative of the current I, which is itself the time derivative of charge Q, should remind you of acceleration. Let's say that we have a simple circuit with a battery, a capacitor, a resistor, and an inductor. I'm going to assign the current flow to be clockwise, which means that my sign convention is this. Kirchhoff's voltage law says that the sum of the voltages around the circuit must be equal to 0. Therefore, I get VC plus VR plus VL is equal to VB. Now, if I substitute in the constitutive laws, I get 1 over C Q plus R Q dot plus L Q double dot is equal to VB. I get a second-order differential equation. It is hopefully clear that L here is playing the role of mass in this differential equation. I can rewrite this differential equation in first-order form. Q dot is equal to I, and I prime is equal to minus 1 over LC Q minus R over L I plus VB over L. And then I can rewrite that equation in matrix and vector notation using W equals QI. So I get d dt of the vector QI is equal to 0, 1, minus 1 over LC minus R over L, all times that vector QI, and then plus the vector 0 and VB over L. This means I can use Euler integration from lecture 4 to compute a solution. For instance, if I choose the initial condition to be Q0 I0 is equal to 0.50, and if I choose the constants to be L equals R equals C equals 1, and maybe a voltage of a 9-volt battery, then I get that Q at time 0.1 and I at time 0.1 are approximately equal to the initial condition, which is 0.50, plus the time step, which is 0.1, times the right-hand side of the differential equation, 0, 1, minus 1, minus 1, times the initial condition, 0.50, plus this vector here, which is 0, 9. Now, that is equal to the vector 0.50 plus 0.1 times the vector 8.5, which is equal to 0.5 and 0.85. Now, I can also solve for this differential equation analytically, the way that we did in lecture 5. If I guess an exponential solution for Q of t is equal to e to the ht times w, I get that h squared plus r over lh plus 1 over lc is equal to 0, just like we did with mechanical systems. If r equals 0, that implies that h is equal to plus or minus the square root of 1 over LC times j. Hopefully that reminds you that that will give you a cosine at a frequency of 1 over square root LC and a sine at a frequency of 1 over square root LC. This means that this circuit will have the charge in the capacitor oscillating for all time. That is, the charge stored by the capacitor will fluctuate forever. Now, if I have R not equal to 0, then I can use the quadratic formula, just like we did with mechanical systems, to solve for h. Let's set L equal to 1 and C equal to 1. Then we get R not equal to 0 implies that h is equal to minus R plus or minus the square root of R squared minus 4 all over 2. That means that if R is greater than 2, we're overdamped. That means no oscillations. Whereas if R is less than 2, we're underdamped. And you should expect decaying oscillations as a function of time. I hope that this has convinced you that electrical and mechanical systems have very similar behavior. This is because the equations governing their behavior are exactly the same in many cases. So what should you remember from today? When I have a circuit that has electrical components that include capacitors, resistors, inductors, and batteries, I should expect the same kind of behavior that I might see in a mechanical system that has springs, dampers, masses, and external forces. Also, all of the mathematical tools that we have developed for mechanical systems are also applicable to electrical systems.